must be in Kelvin scale. Okay? For ideal gases, if you have a multiplication, if you have a division, the temperature must be in Kelvin scale. Okay. If we can remember that, write down with a star. Okay. Remember that. You may lose 1 mark, not significant loss, but you know, try to get as many as possible. Is that right? That's the second law. First law applications to the closed systems. But what are the closed systems? Okay, that's some examples. Okay, and I mentioned if you still don't understand or fully understand quiz 1, you have to go back. Okay, and then additional to that, you need to understand the second law. Application of the second law to closed systems. And so I shouldn't repeat why for this system, you know, the heat transfer is equal to the enthalpy change. As I mentioned about enthalpy change, always quite often associated with moving boundary, right? With work transfer. Okay. So that's why in the first law energy equation, some of the terms they have internal energy change, and other terms enthalpy change. Okay. For mass transfer across boundary, okay, so the energy change is related to enthalpy change. And for system energy change, it's internal energy change. So that's for closed system. And then we look at open systems. Basically, you know, we have most examples there just for these 2 typical processes. One is called steady state static flow process. The other one is transient process. Steady state static flow process, including we have had examples like turbines, compressors, pumps, nozzles, diffusers, heat exchangers including closed style heat exchangers and open style heat exchangers. Okay, and you have had you know, some preparation for heat exchangers for most of them, and plus don't forget the slaughtering process, because yesterday in the refrigeration cycle, you know, slaughtering process is one of the 4 major processes in the refrigeration cycle. So we prepared all the knowledge before we started the power cycles. Okay, we analyzed, applied the first law, second law to different processes for open systems, for closed systems, for steady state flow process, for transient process. Transient process, we haven't done very complicated questions, either mass in or mass out, right? Yeah, we haven't. You know, there can be complicated questions like with moving boundary, you know, power, you know, pump work across the boundary can be like that. But you know, I believe I have simplified the questions for you. Okay, so transient process deal with 2 flows with mass in or mass out. Okay. Okay, for open systems, we need one more tool, okay, which is the mass continuity. Okay, don't forget that, because for any questions, we try to find the right tools to solve the problems. Okay, right tools. That's very important. That's why how, you know, just like we have many tools, spinner and hammer, whatever. When we should use the right tools for what? Okay, that's what we are learning in thermodynamics. All the equations, they are tools, and we need to understand when they should be used. Okay. So first law, second law, and mass continuity. Okay. And the first law, energy equation, we just come back to transient process. Okay, maybe transient process first. Okay, if the process is from state 1 to state 2, that's the energy equation, comprehensive energy equation. Do you have any question, David? No? No? Okay. I saw you raise your hands. Yeah. Both hands. Yes? This one? Yeah. I already photocopy scanned, because before I came to class, UPS online just temporarily not working. Have the upload. If you don't see that tonight, just send me. It's very easy for me to forget things. I haven't forgotten many things in this class, but I have forgotten attending some meetings, some important meetings. I just record after the meeting already finished. That's very bad. Okay, so that's the comprehensive energy equation. Okay, and then how to simplify this equation? That's the key point. Okay, how to simplify? That's the key point. For I think in study guide, I didn't. Oh, not this one. Okay. So that's the examples. You know, compressors, turbine. Okay. And please notice we can't, just use this straight away. Depends on the conditions. What's the conditions? Conditions here, kinetic energy change, potential energy change ignored, right? And then only one single mass flow rate. That's why the energy equation can be divided by the constant mass flow rate and then become a specific energy form, okay? So it's not, and for this part, and the turbine, gas turbine, steam turbine, okay, you still need to understand, how to apply the first law and the second law. And the second law basically is isentropic efficiency, okay, for compressor and this turbine. So that's quiz 3. Unfortunately, even you have done, lab report too. I saw that everyone did the report and you should remember the isentropic efficiency, but unfortunately, most people didn't. Yeah. So that's why, quiz 3 really disappointing, and I hope final exam won't be like that. Okay? Will be much better. Okay. And I think what I want to say is the transient process, I only put one system here. There is another one with only mass leaving the system. Okay, so for this one, that's the simplified. You can see from here to here. Why? Because change of kinetic energy, change in potential energy, or ignored. And also we define, the system is defined by this thick black line, okay? And then, because there is no moving boundary, what are the moving boundary? 3 types of moving boundaries. Physically moving boundary, like the moving piston, okay? If the piston is moving, that's moving boundary. Second, rotating shaft cross boundary, right? That's equivalent to moving boundary. And the third one, electricity power supply cross boundary. Okay, so 3 types of moving boundary for you to identify the defined moving boundary in thermodynamics. Okay. So work transfer is 0, no moving boundary. That's what's left in this equation. Okay, in this equation. Okay. And sometimes if just like if it's gas, okay, the filling process is very fast, and then sometimes can be the heat transfer can be ignored. But if the heat transfer is asked in the question, we can't ignore the question. Yeah, I've seen some exams like that. The question asks heat transfer, and heat transfer is ignored. If the heat transfer is ignored, it means the question is ignored. So you don't need to do any solution. So don't ignore the questions. If the heat transfer even is zero, we still need to show why. But normally, if the heat transfer is asked as a question, it's not zero. It means the process is not adiabatic. Okay? I think the problem I feel a little bit worried is I haven't written. You should write. I think even I haven't written because I can't write so much. I've already written before I came here. So you should make some notes for the things important to you. You have forgotten, and you must remember. Okay. So for transient process, that's and also mass continuity. Okay, mass continuity. For example, M2 is equal to M1 plus Ni. Final mass in the tank should be equal to the mass originally here and plus mass flow in. Okay, and then because the mass flow in is constant state, so the state is not changed. Even it's changing. For example, I promise we don't go to any particular examples yet. If it's gas, it's leaving the system, actually the properties change. And in that case, we use the average property from the initial and the final state. Okay, one of the examples in the study guide. Okay, for another transient process. Okay, with only mass leaving the system. And then we come back to the steady state, steady flow process. Steady state, steady flow process. I think the first law, in which conditions, how to simplify the first law energy equation is already here. Okay, that's for a nozzle. And for heat exchangers, open style heat exchangers and closed style heat exchangers. Okay. Okay. And then the application of the second law. Okay. For transient process. Okay. Second law. Let's go to the section. And the equations like that, okay, the reason I highlight them just because these two conditions must be met. That's for ideal gases, okay? Must be ideal gas. If you apply this to steam refrigerant, most likely you will get the solution wrong, okay? So, and the process must be isentropic. Even it's a adiabatic process, you still can't use it. Must be reversible and a adiabatic process, okay, to use the equations like that. Okay, isentropic efficiency of the turbine, actual power divided by isentropic power, okay? And the compressor, just the opposite, because the compressor is a device which requires power to drive. So the one which requires less power to drive is more efficient. Okay, so that's the isentropic compression power divided by the actual power. Okay, I kept this Q here just for the energy loss. Okay, additional to the enthalpy change. Okay, can be gain, can be loss. Normally it's a loss. Okay, just to avoid. Otherwise, people all think all the process there, all the process happening in the turbine, in the compressor there, adiabatic process. But in practice, they are not. Okay, it just depends on how significant they are. So you still need to understand the isentropic efficiency. Okay. Okay, and then to calculate the rate of entropy generation is for steady flow process. We know because there is no mass accumulation in the system. That's why the system energy change is zero. The system property change, energy change is zero. Okay, so we can only measure the mass flow rate. Okay, that's why all the terms they are in rate form, unless you can divide all the terms by mass flow rate, and then that will become, specific entropy change or whatever, specific entropy change, specific internal energy change. Okay, total entropy change for the rate of entropy generation in the steady flow process is equal to rate of system entropy change, because for open system, plus the rate of entropy change in the surrounding. Okay. And this is for steady flow. And one of the assumptions, that's from one of the assumptions, major assumptions for steady flow process, the system energy change is not a function of time. The rate means first order differentiation with respect to time, right? So that's why this term is zero, okay? And the surrounding entropy change, here I just change the name from here to here, they mean the same thing, okay? Or I equal here. I just try to, I don't like to call something with different names. That's what I tell my PhD students when they write the paper. Don't give different names for the same thing to confuse the readers, okay? Simplify here. But anyway, the textbooks have the different names, then you have to follow. Okay. So it's equal to the entropy change due to mass transfer across the boundary, must be crossing the boundary, plus the entropy change, minus the entropy change due to the heat transfer. This negative sign, as I explained quite a number of times, because this heat transfer is obtained by applying the first law to the system. So to the system is positive, to the surrounding must be negative. To the system, negative, to the surrounding must be positive. Okay, that's why the negative sign is here. Okay, and then for detailed systems, for all of these open systems, okay, turbine, compressors, and then diffusers, okay, nozzles, and the heat exchangers. Oh, that's the second law. Okay. Then we need to understand okay, for all these open systems listed in section 2, okay, how to calculate the entropy change, okay, from the mass transferred across the boundary. Okay, for water and the refrigerants, you can find out the entropy by knowing two independent problems, right? But how to do that for ideal gases, okay? And actually there are two different ways. One is assuming constant CV, and the other one is using table 8.7.1. All of this you already had experience from your quizzes. Okay. So for all of these open systems, you need to understand how to calculate this term and how to calculate this. Sometimes you need to combine something, because for Okay. Because for ideal gas, okay, for ideal gas, if you want to use